When an embankment, foundation or retaining wall fails, it is due to shear failure taking place in the surrounding soils. In this chapter, we will discuss shear strength of soils. If this slope is too steep or too high, a section of the soil mass slides down along a failure surface, and the slope is deemed to have failed. What has happened is that the shear stress along the failure surface has exceeded or became equal to the available shear strength. Along the failure surface, the soil grains slide over each other, thus moving the entire soil mass that is sliding. It requires much larger stresses to crush the soil grains, and let's not worry about that here. We will only discuss shear failure. We will be using the Mohr's circles. You would have studied in engineering mechanics or strength of materials. In soils we will take compression as positive and the shear stress axis points upwards. Just the upper half of the Mohr's circle is enough for our work. We denote the major and minor principal stresses as sigma 1 and sigma 3, respectively. Mohr's circle fully defines the state of stress at a point. Every point in the body is under different stresses and hence requires separate Mohr's circle. We still can draw many Mohr's circles, representing different points in the same sigma tau space. From red to green, we turn counterclockwise by an angle alpha at a point A. To represent them on the Mohr's circle, we rotate by 2 alpha counterclockwise, when we go from red to green. Here is an example on how to draw the Mohr's circle for a given state of stress. The first step is always to find the radius and center coordinates, which enable us to draw the Mohr's circle. Once the Mohr's circle is drawn, Identify the horizontal and vertical planes on the Mohr's circle. Here, the sign convention for shear stress comes in when deciding on positive or negative shear stress. From here, it is geometry and trigonometry. Here, we ask you to deduce the Mohr's circles and the principal stresses, without any serious calculations. Otto Mohr, who introduced Mohr's circle, suggested that shear strength along the failure plane is a function of the normal stress acting on the same plane. The relationship between the two defines the failure envelope. We denote these values by tau f and sigma f, with a subscript f. As you can see from the failure envelope in the figure, larger the sigma f, larger is the tau f. Coulomb in 1776 noted that shear strength has two separate components, frictional and cohesive. Combining the ideas of Mohr and Coulomb, Mohr-Coulomb failure envelope is defined as tau f equals sigma f times tan phi, plus c. Here, phi is the friction angle and c is the cohesion. The equation of the failure envelope is a straight line. The frictional component is proportional to the normal stress. The cohesive component remains the same at all stress levels. Granular soils have no cohesion and hence C equals 0. Therefore, tau f equals sigma f times tan phi. The failure envelope passes through the origin. This is a very useful chart from the U.S. Navy, for estimating approximate values for the different granular soils, in the range of 26 degrees to 44 degrees. You can see that the friction angle increases with relative density, angularity of the grain, and grain size. Well-graded soils give higher friction angles than poorly graded ones. Presence of water reduces the friction angle very slightly by 1 or 2 degrees. Here is another rough guide to estimate the friction angle of a granular soil, allowing for contributions from angularity, grain size distribution, and relative density. Here, the possible range is 30 to 47 degrees. This is about a slope failure, with the failure surface shown in red. Point A is on the failure surface and hence its Mohr circle is touching the failure envelope. Points B and C are not on the failure surface and therefore the Mohr circle would be within the envelope, without touching it. The point B within the soil mass is initially under an isotropic stress of sigma c acting all around. The Mohr circle is given by a point. Let's say that an additional vertical stress delta sigma is imposed at B and the diameter of the Mohr circle becomes delta sigma. Now, if the delta sigma is increased, the Mohr circle expands on the right until it touches the failure envelope when there is failure at B. At failure, we denote delta sigma as delta sigma F. Let's have a good look at the Mohr circle at failure, which has radius of half delta sigma F. Note the orientations of the horizontal and vertical planes on the Mohr circle. Failure corresponds to the point F on the Mohr circle, which implies that the failure plane is oriented at an angle of 45 plus half phi to the horizontal. Sigma F and tau F are the normal and shear stresses acting on the failure plane. Let's look at point A where we have shown the total stresses, effective stresses and the pore water pressure. Here, we can draw separate Mohr circles in terms of total and effective stresses. They are of the same diameter, separated horizontally by a distance u. Here, we have three identical soil specimens, subjected to different isotropic confining pressures sigma c. Each specimen is subjected to an additional vertical stress, which is increased until failure occurs under delta sigma f and pore pressure of uf. From these values at failure, we can draw two sets of Mohr circles, in terms of total stresses and effective stresses, and establish the failure envelopes in terms of total stresses and effective stresses. We use a prime or dash for the effective stress parameters. It is very important to understand the significance of drained and undrained loading in clays. After a long time since loading or when the loading is very slow, there is no excess pore water pressure and the clay is fully drained. With the effective stresses determined relatively easily, it is possible to carry out the analysis in terms of effective stresses, using C' and Phi'. Immediately after loading or when the loading is sudden, there is buildup of excess pore water pressure and the effective stresses are unknown. Here, we do a total stress analysis, using Cu, and Phi-u equals 0. We are not separating the soil grains and water and treat the soil as one material. Granular soils are generally assumed to be free-draining and hence analyzed in terms of effective stresses. Now that we have shear strength parameters in terms of total and effective stresses, how do we determine them? How do we simulate drained and undrained conditions for clays in the laboratory? Triaxial test is the most popular laboratory test to determine the cohesion and friction angle of a soil specimen in the laboratory. We test a cylindrical soil specimen, held within an impermeable membrane, surrounded by pressurized water in a perspex cell. A piston at the top is used to apply the additional vertical stress delta sigma, which is increased to failure. You can see the soil specimen enclosed within a membrane, and O-rings at the top and bottom. You can also see the drainage lines that are used for carrying the water, and the cylindrical perspex cell. We generally test 38 to 50 mm diameter soil specimens, which have height to diameter ratio of 2. The drainage valve can be open or closed to control the drainage during the test. Triaxial test is carried out in 2 stages. In the first stage, we apply an isotropic confining cell pressure sigma C around the soil specimen. If the drainage valve is open, the specimen gets consolidated. If the drainage valve is closed, the saturated soil specimen does not get consolidated and remains at the same moisture content. In the second stage, we apply the additional vertical stress delta sigma and increase it until the specimen fails. During this stage, if the drainage valve is open, the loading is said to be drained; if closed, it is undrained. Depending on whether the drainage valve is open or closed during the 2 stages, we generally go for 3 types of triaxial tests. There are consolidated drained, consolidated undrained, and unconsolidated undrained triaxial tests. They serve different purposes. In a consolidated drain test, the drainage valve is open in both stages of the test. The test is analyzed in terms of effective stresses, and C' and Phi' are determined. In a consolidated undrained test, drainage is allowed during the first stage, allowing the specimen to consolidate. The additional vertical stress delta sigma during the stage 2 is applied with the drainage valve closed under undrained condition. Due to the poor water pressure buildup during the undrained loading, the total and effective stresses are not the same. From this test also C' and Phi' are determined. This is faster than a consolidated drain test. Unconsolidated undrained test is the quickest of all tests but is for different purpose. You cannot determine C- and phi- from here. Since the pore water pressures are not measured, effective stresses remain unknown. The test is analyzed in terms of total stresses, to find the undrained shear strength Cu. This test is mainly for clays. For saturated soil specimens, the failure envelope in terms of total stresses is horizontal, implying phi equals 0. We give a subscript U for the cohesion and friction angle here, implying undrained conditions. Cu is known as undrained cohesion or undrained shear strength of the clay. While we have different Mohr's circles in terms of total stresses, the one in terms of effective stresses is the same for all specimens. When we do a CD or Cu triaxial test, we can determine C- and phi-, which are effective stress parameters. From a UU triaxial test, we determine Cu and note that phi-u equals 0, which are total stress parameters. When do we use what parameters? In clays, undrained loading is assumed during the very early stages of loading or when the loading is quick. These may be analyzed using total stress parameters, Cu, and phi-u equals 0. In clays, long time since loading or during very slow loading, drained conditions are assumed, and the analysis is usually in terms of the effective stress parameters, C- and phi-. Unconfined compressive strength test is a special case of UU triaxial test. On rock or concrete specimens, this is called uniaxial compressive strength test. This test does not require the sophisticated triaxial test setup. It just requires that the specimen has to be able to stand unsupported, without any confining pressure. There is no confining pressure during the test. That is sigma c equals 0. The vertical stress delta sigma is increased until the specimen fails, and the failure stress is known as unconfined compressive strength or UCS, denoted by Q sub U. In terms of total stresses, the failure envelope is horizontal and hence Cu equals half Qu. The term unconfined compressive strength applies to clays only. In the field or on laboratory specimens, it can be crudely estimated by a pocket penetrometer or laboratory vane. For normally consolidated clays and granular soils, C-0. For normally consolidated clays, phi- decreases with increasing plasticity index. For over-consolidated clays, C- can be as high as 25 kilopascals and can be estimated as 10% of Cu. Some typical values of phi- and C- are shown here. From the value of Cu, the clay can be described as very soft, soft, medium, stiff, very stiff, or hard as shown here. There are several ways to determine the undrained shear strength of a clay, Cu. The empirical equations give a rough estimate at no cost. Pocket penetrometer, Torr vane or laboratory vane can be used for an estimate of Cu. UU triaxial test or a UCS test in the laboratory can be a good way of determining the Cu. Vane shear test is also quite an effective tool in the field for determining Cu. Direct shear test is mostly carried out on granular soils but works well on clays too. A 60 mm by 60 mm square circular specimen is subjected to a normal stress, and the horizontal stress is increased until the failure is forced along a horizontal plane separating the specimen box. From 3 or more sets of normal and shear stresses at failure, the failure envelopes are established and the cohesion and friction angle are determined. Loose granular soils and normally consolidated clays behave similarly. They keep compressing until they fail. Dense granular soils and over-consolidated clays show similar behavior when loaded. They compress initially and then expand. Failure can be defined in different ways. The peak values generally occur at relatively lower strain in the order of less than 2%. Critical state is reached at strains in the order of 10%. Residual state is reached at strains in the order of 100%. The values of C- and phi- are different for peak, critical state and residual state. clay fabric is destroyed at large strains and hence C' is 0 for residual and critical states. Phi' is the maximum for the peak and the minimum for residual. Generally, the strains are relatively small in most geotechnical problems and we use peak values in the analysis. Only for large strain problems such as slope stability or landslides, critical state or residual values are appropriate. You saw this before for granular soils. Only addition is that, when the granular soil reaches the critical state, there is no contribution from relative density. Skempton introduced this simple expression to determine the pore water pressure change in a clay under undrained loading where the changes in the principal stresses are known. The B parameter is a measure of the degree of saturation and is about 1 for fully saturated clay. The A parameter depends on the stress history of the clay. At failure, it is denoted by A sub F, which is in the range of 0.5 to 1.0 for normally consolidated clays. For heavily over-consolidated clays, AF can be as low as negative 0.5. The pore water pressure change delta U has two separate components. The first one is due to the isotropic confining pressure change, and the second one is due to the change in deviatoric stress. Also, note that delta sigma 1 and delta sigma 3 are the algebraically largest and smallest values of the changes, respectively. They are not necessarily the changes in sigma 1 and sigma 3, respectively. Skempton's pore water pressure equation is all about changes, relating the changes in the principal stresses to the change in pore water pressure. The initial values do not come in the picture. Stress path is a neat way of keeping track of the progress in the loading at a point. Here, we will assume that sigma V is larger than sigma H, and the pore water pressure is U. We define S and T as S equals half of sigma V plus sigma H, and T equals half of sigma V minus sigma H. While we represent the state of stress by a Mohr circle in sigma tau plane, we represent this in SD plane by a stress point. Note that the coordinates of the stress point is the same as that of the top of the Mohr circle. When we have too many Mohr's circles in the sigma tau plane, they can be cluttered. Stress path, which simply connects the stress points, looks a lot neater. The failure envelope in sigma tau plane becomes a straight line on SD plane, with intercept of secas phi on the t-axis. The slope of the line is tan alpha, where tan alpha equals sin phi. It is relatively easy to prove this. Similar to sigma equals sigma dash plus u, here, s equals s dash plus u. Note that t is the same as d dash. Back pressure saturation is a common technique we use to ensure the soil specimen is fully saturated. We apply the back pressure U0 through the drainage valve during the isotropic consolidation under the cell pressure sigma c. The pressurized water in the cell dissolves the entrapped air pockets.